All right, welcome back. This is going to be fluid mechanics homework number three, and this will be part A. So the problem statement for part A states a cylindrical caisson with no external air supply, an open bottom, and internal height small h is submerged in water. Derive an expression for the depth of water small d that floods into the caisson when it is submerged to a depth big H as measured from the water level to the bottom of the caisson. So the first thing I'm going to do to start solving this problem is I'm going to draw a diagram so you can get a better understanding of the caisson that we're talking about in this problem. So here we have our cylindrical caisson, and it's resting above the water. This is before we drop it in. And the bottom of our water will be right here. So this is our bottom. And this has a depth of big H. And the cylindrical caisson has a height of small h. Now, for this problem, we're going to drop our cylindrical caisson into the water, therefore increasing the pressure inside of the caisson to keep the water out. But as you can imagine, water will be trying to enter the caisson from each side. And when the caisson begins to fill up, we're going to call this depth of water that fills up small d. So, what is similar about these two caissons? So, the caisson above the water, before we drop it in, it has its own volume, it has its own temperature, and it has a number of moles of air inside of it. We're going to call that N, and it also has its own pressure. Um, However, when we drop the caisson in, everything, um, this has a different volume due to the water filling in, a different temperature due to the temperature of the water, a different pressure, but it also has the same amount of moles of air as before it was dropped in, so N is still the same. Now, for this problem, we're going to use the equation of PV equals nRT, and we can compare these two scenarios because N is the same for both situations. So we get P1 V1 over RT1 is equal to P2 V2 over RT2 equaling N. Um, but we also need an expression for the pressure on the inside and also the outside of the container. Because remember, for this water to stop filling up inside the container, the pressure on the inside of the container has to equal the pressure on the outside. So on the outside here, at this depth, we're going to have P1, so the pressure before we dropped it in, plus rho GH. And the pressure on the inside of the container is going to be equal to P2 plus rho GD for the depth here. And these two are going to be equal to each other. Now, if we think about the volume as a area times a height, um, and the height in this case being small h, we can help simplify this equation a little bit more. So we get P1 A times H over, and the R's cancel here actually. So T1 equals P2 A, and the height in this case is going to be the height of the caisson minus small d here because of the water filling into it. So we get H minus D over T2. And we're going to try and solve for P2 here to help simplify this equation. So we get P1, the A's cancel, H T2 over T1 H minus D equals P2. And we're going to replace P2 into our equation up here. So we get P1 plus rho GH is equal to, and remember it was P2 plus rho GD. So we're going to replace P2 as P1 H T2 over T1 H minus D plus rho GD. And we're going to call this term alpha and this term beta to make it simpler to simplify. So our next step, alpha H minus D is equal to beta plus rho GD. And then we get rho GD squared minus alpha plus rho GH D minus alpha H minus beta equals 0. So we get D is equal to alpha plus rho GH plus or minus the square root of alpha plus rho GH squared minus 4 rho G all over 2 rho G. And this is our expression for the little d, which is the water that fills in the height.